Okay, so let us start today's lecture. Uh, some more people may join in a bit later, but I think that's almost all of us. Okay, so today is essentially going to be the last, the second last lecture, so to speak, on this section on curvature as well as on the whole course itself. So we're going to talk about two special quantities associated to Riemannian manifolds called the Ricci curvature and the scalar curvature. And in the next lecture, I plan to, again, the next lecture is not going to be officially part of the syllabus, but it's going to be one of those lectures where I'll try to talk about what interesting theorems have been proven using restrictions on curvature, and what are some classical highlights of this subject, and what one can do with these notions. Okay, that's going to be the next lecture, and then after that, depending on interest, I might hold a tutorial session. Okay, so let's start. So we want to talk about two different things, and they're related but not quite the same as sectional curvature. Remember that sectional curvature was still a more tractable version of the Riemannian curvature. The Riemannian curvature was a huge gadget. Sectional curvature seemed less daunting, but it still was a lot of information. However, sectional curvature and Riemannian curvature, each one determines the other. So that was a good thing. So now we're going to talk about first the Ricci curvature. Okay. So, and if you read through Spivak's book, volume 2 of the Comprehensive Introduction to Differential Geometry, he mentions that even though when Riemann defined his curvature, he defined it the way we define it nowadays with RIJKL. However, he didn't probably realize fully that what he was defining was a tensor, although he wanted all those same properties, essentially because the classical notion of tensor did not even exist in the time when Riemann discovered his curvature tensor. Okay. In the subsequent years, Ricci had a lot to do with the development of the calculus of tensors, and later on also his student Levi-Civita, as you have seen being attributed to the notion of Levi-Civita connection, worked on this notion. Okay, so this is early 1900s, I think. Anyway, so Ricci is also associated to a special kind of curvature, which is a very specific combination of sectional curvatures cooked up in a certain way. But the reason why it's very famous and important is that this Ricci curvature appears very frequently in a lot of places. It appears in physics, meaning general relativity. It appears in geometry, of course. It appears in a lot of other contexts, as you'll soon see. Okay. Okay, so let's start with the definition. And as we have been accustomed to, this is going to be a definition which is a computational definition. Very soon we're going to show that this computational definition is actually well defined and independent of the choices. So let X be a unit vector and choose an orthonormal basis Z1, Z2 up to Zn minus 1 along with X of TPM.
Sir,
yes.
When you say independent of choice, you mean independence of choice of the chart, local chart?
No, I'll say what do I mean. So here there's no chart at all. So I mean, you'll see what it is it will be clear in the context. Okay. So it could mean lots of things. I mean, if I'm, anyway, I'll get to that. Let me define it first and then I'll say what it is. Okay. So yeah, so we start with a unit vector in the tangent space at P. You extend this to an orthonormal basis. That simply means you choose an orthonormal basis Z1, Z2, Zn minus 1 along with Zn, the last vector being X. You can always do this. So now the Ricci curvature of the manifold M in the direction of X at the point P is defined to be this quantity. Okay? So we write Ricci, RIC, short for Ricci, at the point P in the direction of X to be an average. There's a scaling factor of 1 over n minus 1. This is a sum over the usual sectional curvature. Remember the usual sectional curvature of two vectors if they're linearly independent, if it was an orthonormal basis x comma y spanning a two plane sigma, then the sectional curvature of the plane sigma was rxyx dotted with y. So this is precisely that. This is the sectional curvature of the two planes spanned by x and zj. You take the sum over j and you divide by n minus 1. The reason why you divide by n minus 1 is that when j is equal to n, x is already zn. So r of zn, comma zn, that is simply 0 by skew symmetry. So you really have potentially n minus 1 sectional curvatures that appear, namely the sectional curvature of zn along with any of the z1 through zn minus 1s, and then you take the average of that. So that's essentially what the Ricci curvature in the direction of x is defined to be. Okay. And the scalar curvature at P, so this has no direction involved. This is just a quantity defined at a point P, is defined to be the average of the Ricci curvature. So you take the Ricci curvature in the direction Zi at P, and then it's 1 over n. Okay, so here when I write 1 over n, there's a sum. Okay, so this simply means there's a sum. Okay, so I've forgotten to put a summation I, but this is a sum over the Ricci curvature along Z1, along Z2, along Z3, up to along Zn. You divide by n because there are n terms. So if I expand using the previous formula, which is here, what I get is 1 over n into 1 over n minus 1 into the sum of the sectional curvatures. Okay. But of course, there's a bit of overcounting here because r zi zj is equal to r zj zi. But nonetheless, okay. So these are the two definitions that we will be talking about exclusively today. Okay. Okay. So the natural question here is we defined a quantity in the direction x or at a point x by using an orthonormal basis. So the first question that you should ask is, this should really not depend on the orthonormal basis, meaning if I choose another orthonormal basis extending x, calculated using that basis, the two answers should match. Correct? That's what well-definedness means here. Okay. And that's what we're going to show as the first step, to say that these are really well-defined quantities. Okay. So any questions before we do that? Okay, good. So as pointed out in a lot of books, in particular in Docarmo, for which will follow the, and part of this exposition, the best way to prove these definitions are independent of the choices is to give an intrinsic characterization of the quantity. So if you can somehow intrinsically give a definition of the Ricci at P in the direction x and the scalar curvature at P using some other means, then this simply becomes a way to compute that intrinsic quantity, and hence well defined. Okay. So towards that, let's consider a linear map which is dependent on two variables x comma y. So choose two vectors x comma y in the tangent space. You consider the linear map given by this. So this is a linear map which, for a fixed x and y, it's a map from TPM to TPM. Well, what does it do? It sends a vector z to r of x comma z acting on y. Okay. So again, to make sense of r of x comma z acting on y, you have to extend x, z, and y to local vector fields, and then this is simply the Riemann curvature acting on y and then restricted to P. But as you have seen, the extensions don't matter when you calculate. So that's why this is a well-defined thing. But to actually make sense of r, x, y, z, r, x, comma, z acting on y, you have to extend x, y, and z to local vector fields and then restrict that value at P. Okay. But the upshot is that this is a linear map. Why? Because r, x, y, r, x, z, y, w, r is a tensor, so it's linear in all the four slots. So in particular, it's linear in the slot for z. So it's a linear map, okay, for every fixed x, y. Good. So this is a map which is very natural. It's already there. We have talked about it and we have used this to compute the RIJKL. So, but this is a map that you know. Okay. So now what do you do? Well, we can take the trace of this to obtain a bilinear form on Q. So what do we mean by this? Remember, this L is a linear map from TPM to TPM, but L itself depends on two quantities, x comma y. So if I take trace of L, What should that be? See, L is a linear operator from TPM to TPM, so the trace is going to be a real number, right? So trace of LXY is a real number. So for every pair x comma y, I'm getting a real number which is trace of LXY, and that defines a bilinear form Q on the tangent space, right? This. So why is it bilinear? Well, it's bilinear because it's linear in x and it's linear in y, and that is because the Riemann curvature tensor is linear in all the 4 slots. Okay? So that's because R is linear in each of the 4 variables, here 3 variables. It follows that Q is indeed a bilinear form. Okay? Any questions so far? Okay, so this is all very intrinsic and canonical. There's no choices that we are making. We just use the Riemann curvature and then we just define this Q. So associated to Q, you can do two things. Okay, one of two things. You could say, okay, if I calculate Qx comma x, whatever Qx comma x is a well-defined quantity. So Qx comma x, if I happen to show, is equal to some multiple of the Ricci curvature in the direction x, then that tells me that the Ricci curvature as defined earlier is well defined because it's simply a multiple of Qxx, and Qxx is well defined. Okay, so let's do that. So that's what we're going to do. Okay? So let's take an orthonormal basis of TPM Z1, Z2, Zn, and let's calculate Q of xy. So what should Q of xy be? So remember, Q of xy is nothing but the trace of the linear map given by L of xy. So if I have a linear map L from V to V, V is an inner product space, how do I calculate the trace? Well, I basically choose an orthonormal basis, V1 through Vn of V. I calculate L of Vi dotted with Vi, sum over I. That's the trace of L, correct? And this is independent of the orthonormal basis that you choose. This is how you calculate the trace. So here we choose an orthonormal basis of TPM, and the trace of LXY is nothing but LXY acting on Zi dotted with Zi, sum over I. But that simply by the definition becomes R of XZI acting on Y dotted with Zi, sum over I, 1 through N. Okay? Is this clear? So I'm just recalling something very basic from linear algebra. The way to calculate the trace is by a choice of an orthonormal basis, and then you calculate L of Vi dotted with Vi. Okay. But because of the symmetry of the Riemannian curvature tensor, you could swap the YZI with the XZI, and it's the same answer, right? This is one of the symmetries of the Riemann curvature tensor, that I can swap the last 2 slots entirely with the first 2 slots. Okay, so this is what you get. But what is this quantity? This quantity is nothing but QYX, correct? So because of one of the symmetries of the Riemann curvature tensor, what you observe is that Q is actually not just a bilinear form, it's a symmetric bilinear form, right? Q is symmetric. So that's actually going to be very helpful, and in fact, almost necessary for what we're going to do later. Okay, any questions so far? Good. So what we have so far is something very canonical, starting with a manifold with a metric. You have the Riemann curvature tensor, you define L, take the trace that gives you a bilinear form Q, and this bilinear form Q is actually symmetric. Okay, good. So we now want to get back to the Ricci curvature and the scalar curvature. So recall that in the setup, we had X to be a unit vector, and this was extended to an orthonormal basis, Z1, Z2, Zn minus 1, along with X equal to Zn being the last element of the basis. Okay? So this is our orthonormal basis, and let's calculate Qxx. How do I calculate Qxx? Well, this is nothing but the trace of the linear map given by Lxx. But how do I calculate the trace? Well, we just said this is nothing but calculate Lxx acting on Zi dotted with Zi. But that is nothing but precisely the sum of these sectional curvatures, right? Rx Zi acting on X dotted with Zi, sum over I equal to 1 through N. Okay. Okay. But what are these? Remember, these are just the sectional curvatures of the plane spanned by X and Zi. Okay. So this is nothing but n minus 1 times the Ricci curvature at P in the direction x, because this is how a Ricci curvature was defined, right? That you extend x to a orthonormal basis and then you calculate this up to a factor of 1 over n minus 1. So the Ricci curvature in the direction x is nothing but 1 over n minus 1 of qxx, and because qxx is well defined, Ricci curvature is well defined and independent of the orthonormal basis.
So, sir, when you say that it's independent of choice, by choice you meant independent of the choice of the orthonormal basis, right?
Yes, in this case, in this case, that's the choice. Yes, because you're doing everything at TPM. So the original definition required an extension of x to an orthonormal basis, and so you could have shown it directly also that this is independent. But what I'm doing is following a more streamlined approach where we'll prove that the scalar curvature and the Ricci curvature are both obtained from Q, and this Q is really the main quantity that should be of interest if you want to learn more. That's why I want to introduce Q up here, but you could have done it just from linear algebra as well. Okay. But yeah, but the upshot is that it's independent of the orthonormal extension of x in order to define Ricci in the direction of x at P. Yes. Okay. Any other questions? Okay, so good. So this Q actually, as you'll see, will play an important role. So this is saying that Q is, it's naturally there whether you like it or not. And if you take the diagonal values of Q along any unit vector, what you get is simply a scale version of the Ricci curvature in the direction x. Okay. Now what about the scalar curvature? Well, yeah. So in particular, Ricci curvature in the direction x is well defined because it's up to a factor of 1 over n minus 1 qxx. So yeah, so maybe I should mention before I move on, this bilinear form Q up to a factor of 1 over n minus 1 is often called the Ricci tensor because it is a tensor. So it's, and actually it's defined over, you know, the whole Tm, but it's defined over Tm tensor Tm. So for every point P, you have a map from TPM tensor TPM to R, which is this 1 over n minus 1 Q. And because Q is bilinear, it's a tensor. So we will not say much about this tensor in terms of any local analysis. We will make some remarks later on regarding Einstein manifolds, so where this will appear again. But anyway, but for the most part, we'll be interested in calculating Ricci curvature at P in the direction x. Okay. All right. So what about scalar curvature? Okay, so before I go there, this is an exercise. Again, whatever concepts you are learning, it's always good to, you know, see what it means for surfaces, because surfaces is one particular instance of a family of examples where you already know the classical invariants. There's the Gaussian curvature, and that's essentially all of it, pretty much. So whatever invariants you're introducing, you should know how they compare with the classical invariant. So for a surface, let's take the tangent space TP sigma. Sigma is a surface. Choose an orthonormal basis Z1, Z2 of the tangent space. Okay. Then your exercise is to show that the Ricci curvature in the direction Z1 equals the Ricci curvature in the direction Z2, and this is equal to the scalar curvature, which is also equal to the Gaussian curvature. Okay. So for an orthonormal basis, all these quantities are the same. The Ricci in any orthonormal direction is equal to Ricci in the other orthonormal direction is equal to the scalar curvature, which is nothing but the Gaussian curvature. Okay. So this is a simple one-line computation which follows easily from the original definition, the computational definition. So okay, so this says that the Ricci curvature or the scalar curvature is something that you already know. Good. So what about the scalar curvature in general? Why is it well defined? Well, you have a symmetric bilinear form Q, and we had used this method last time. We said whenever you have a symmetric bilinear form Q on a vector space V, which is an inner product space, in this case it's a symmetric bilinear form on TPM, and TPM is an inner product space because the Riemannian metric is an inner product on TPM restricted to P. So that will induce a self-adjoint map from the vector space to itself. So we actually remember we used this last time to get a self-adjoint map from H2 of TPM to H2 of TPM, and we called that the Riemann curvature operator. So here it's the same method but applied to TPM itself. And how do I define this map K? Well, it's defined exactly in this implicit way, that the map K is defined by K of X dotted with Y is nothing but Q of XY. Because the inner product is non-degenerate, I can solve for K explicitly and uniquely, which is defined implicitly by this equation. Okay? So it's the same thing that we used last time. It's the same method that we're using here again. But now instead of H2 TPM, we're applying it to TPM directly. This is again a very commonly used trick from linear algebra. So Q being bilinear gives you this map K which is linear. Q being symmetric tells you that K is self-adjoint. Okay, good. So if you have a self-adjoint map from TPM to TPM, well, you could do lots of things. You could in particular talk about the trace of K, correct? So because whenever you have a linear map, one of the few things that you would want to compute straight away are the determinant and the trace. So the trace makes perfect sense here. Okay, so that's what you're going to do. So are there any questions before we move on to that small computation? So any questions regarding this linear algebraic fact that the symmetric bilinear form on an inner product space can be identified or gives rise to a self-adjoint linear map from V2 itself, and you can go back and forth. Okay, good. So, okay. So the trace of K, how do you compute the trace of K? Well, again, you choose an orthonormal basis, Z1, Z2, Zn. You calculate K of Zi dotted with Zi, sum over I. That's it. So trace of K is a perfectly well-defined object because K is a perfectly well-defined linear map and it comes from Q, and Q is almost canonical, so to speak. So trace of K is well-defined. So how do you calculate trace of K? Well, it's simply this quantity. Well, what is this quantity? By definition, this is nothing but summation Q of Zi, correct? But what is Q of Zi? As we just saw, Q of Zi is nothing but n minus 1 times the Ricci at P in the direction Zi, sum over I. So that's it, right? So this is nothing but n into n minus 1 of the scalar curvature, because remember scalar curvature was defined to be 1 over n of the summation of the Ricci curvatures in the direction Zi, 1 through n. So this is nothing but n into n minus 1 times K of P. Since trace of K is well defined, K of P is well defined as an abstract quantity, and the original definition is a way of computing K of P. But it's also a valid definition now, okay? Okay, so we will see some computations towards explaining these things later on. But are there any questions regarding the well-definedness? Okay, so yeah, so this implies, of course, that the scalar curvature is well-defined because it's a multiple of trace of K, which is well-defined. So this is a nice thing because you are getting everything from Q. You define Q. Q is basically the trace of some map L, which is dependent on 2 parameters. And then you use Q to define a linear map K, and then the trace of K happens to be up to a multiple the scalar curvature. So everything has a very nice, beautiful linear algebraic flavor. Okay? And which is one reason to love this kind of analysis of why things are well defined. Okay? So yeah, so the scalar curvature is simply the Gaussian curvature when you deal with surfaces. In general, the Ricci curvature determines the Gaussian curvature tensor, okay, in dimension 3. So this is not true in higher dimension. This is only specific to dimension 3. In dimension 2, everything is the same as we just saw. In dimension 3, however, the scalar curvature will not determine the Riemannian curvature, but the Ricci curvature and the Riemannian curvatures are one and the same, in the sense one determines the other in dimension 3. And if you are interested in thinking or knowing about this, you should probably attend Ujan's presentation, where he's going to essentially talk about an equivalent version of this. Okay, so this is very specific to dimension 3, and that's why a lot of interesting things happen with Ricci curvature in dimension 3. And we'll get to that at the very end of the talk. In higher dimensions, things are different, but you can still say a lot if you know enough about Ricci curvature. Okay? So I'd like to make a remark. So if you follow Docarmo, then this is the convention that he uses, that the constants are 1 over n and 1 over n minus 1 when we define the Ricci and the scalar. And in Galois, Foulin, Lafonte, or in some of the other texts, those constants are not there. Okay, so there is no scaling of 1 over n minus 1 or 1 over n. It's just defined to be the sum. And there are various reasons to do that. The reason why we chose to follow Docarmo is because with these scaling constants, the Ricci curvature and the scalar curvature agrees with the Gaussian curvature of the surfaces. Otherwise, there would be a factor of 2. Okay, that's the reason to choose this. Was I audible for the last few minutes?
Sir, for the last few seconds, the screen froze.
Oh, so is it okay now?
Yeah.
Okay, yeah. So as I was saying that the remark is that we had some scaling constants while defining the Ricci and the scalar. So for the Ricci, there was 1 over n minus 1. For the scalar, there was 1 over n. So Docarmo uses this convention, and we are following Docarmo. Galois, Foulin, Lafonte, or some of the other texts don't use this convention, so they don't have a scaling factor. And there are reasons for choosing either one. The primary reason for choosing this convention is that according to this convention, the Ricci or the scalar curvature for surfaces exactly equal Gaussian curvature. There is no scaling factor of 2, which would otherwise be there because you're dividing by 1 over 2 when n is equal to 2. Okay? That's the reason for choosing this convention. Okay, anyway. So, okay, so now.
Sir, so in the last lecture on sectional curvature, you said that Riemannian, like knowing sectional curvature, we can determine the Riemannian curvature. So basically, knowing sectional curvature, we have all the information.
Yes.
But knowing Ricci curvature, we do not have all the information, right?
You don't, yeah.
Like,
so only for dimension 3, it is the whole information, but for higher dimensions, is not. Yes. So, I mean that I mean it's a good thing and as well as a bad thing. There are certain things you can do with Ricci curvature, and you cannot do the whole geometry in higher dimensions simply because Ricci curvature is already the trace of something, right? Or along the diagonal, so to speak. So you're already losing information if the dimensions don't match up. And so 3 is the best case scenario, but beyond that, it's really less information than the whole curvature tensor. Yes. So, okay. So let's discuss a couple of examples, and I want to keep discussing this example of manifolds with constant sectional curvature simply because this is it's a nice example to keep in mind, and a lot of the development of Riemannian geometry was motivated by trying to understand class of manifolds with constant sectional curvature. Okay? So this will always occupy a sort of a special place in any text. So let Mg be a Riemannian manifold with constant sectional curvature K. So what does that mean? That means for every point P, you choose a two-plane sigma inside TPM, calculate the sectional curvature of that two-plane sigma by choosing an orthonormal basis x comma y and then calculating r xy xy. That quantity will always be the constant K for all P and all two planes. Okay? Okay. Good. So, okay. So now I want to claim that the scalar curvature is also a constant function and the scalar curvature is always K. So why is that? Well, if you remember, the scalar curvature was the average of certain sectional curvatures, right? But if each sectional curvature is constant, if you take n number of them, add them up, divide by n, it's still the same constant. So that's why the scalar curvature is a constant function. The scalar curvature is the same for all points, and it's the same value K. Okay, this is essentially by the definition of scalar curvature. Okay, what about the Ricci curvature? Well, take a unit vector x, extend it to an orthonormal basis z1, z2, zn minus 1, and x being the last vector, we call it zn. What is the Ricci curvature in the direction x at the point P? It is simply 1 over n minus 1 of qxx. What is qxx? Recall that this is nothing but 1 over n minus 1 sum over the sectional curvature of the plane spanned by x and zi. So here in the sum, although I runs from 1 through n, the only non-zero entry will come from I running from 1 through n minus 1. Because when I is equal to n, x is equal to zn. So r of zn is 0 by skew symmetry. So there's really n minus 1 non-zero terms here, and each of the n minus 1 sectional curvatures are k. So this is again going to be k, correct? We're adding n minus 1 copies of k dividing by n minus 1. So the Ricci curvature is also a constant, meaning for every unit vector at P, the Ricci curvature is k. Okay. So everything is constant. Once you have sectional curvature to be constant, scalar curvature is constant, the Ricci curvature is constant. Okay. Okay. So the exercise for you is to show that the Ricci tensor, remember the Ricci tensor is not 1 over n minus 1 qxx. It is 1 over n minus 1 q of x comma y. So q, remember, is a bilinear form restricted to every point. And if I take the Riemannian metric G restrict to a point P, that is also a bilinear form. It's a positive definite symmetric bilinear form, but it's a bilinear form nonetheless. So the exercise for you is to show that in this particular context, the Ricci tensor 1 over n minus 1 q exactly equals k times the metric G. So these are both, take input as two tangent vectors and outputs a scalar, correct? So they are of the same kind. So the question really is 1 over n minus 1 q is exactly equal to k times G. And 1 over n minus 1 into q was defined to be the Ricci tensor. So this is saying that the Ricci tensor equals a constant times the Riemannian metric. Okay. So we'll come back to this a bit later again, but this is a nice equation to have for various reasons, and I'll make some comments about that later on. Okay, so is the exercise clear? So you just have to compute 1 over n minus 1 qxy and show that that equals k into gxy. And you already know that 1 over n minus 1 qxx is k. So just use the bilinearity of q in both slots, okay, and the fact that q is symmetric. So yeah, so manifolds for which the Ricci curvature is proportional to the metric has a special name. It's called an Einstein manifold, or sometimes the metric G is called Einstein. Okay, so here I'm going to take a slightly different meaning of the word proportional, and just bear with me for a moment. So what I mean here is that the Ricci tensor 1 over n minus 1 q is lambda times G, or if I absorb the 1 over n minus 1 on the right hand side, I'm just wanting q to be lambda times the metric G, where lambda is a smooth function. Okay, that's all. Lambda is a smooth function. Whenever this happens, I call such a manifold Einstein, and oftentimes the Riemannian metric G is also going to be called Einstein. Okay, so the first example of such a manifold is obviously the example that we started with. Any manifold with constant sectional curvature is an Einstein manifold, because the lambda can be taken to be the constant function k into n minus 1 rather. Okay. Okay, so these manifolds are very important, and in particular in general relativity, when you replace the Riemannian metric with the pseudo-Riemannian metric or the Lorentzian metric, these play a very important role. So this is important in physics, for example, these kind of manifolds. Okay. Or even in complex geometry, they are quite important. So yeah, and so for those who have seen these things in physics or know a bit about the GR, so in vacuum, when you're trying to solve the Einstein equation, this is simply given by the Ricci curvature equal to 0. But that essentially is asking you to solve for q is equal to 0, because so because we are working with Einstein manifold, so the Ricci curvature is nothing but 1 over n-1 cube, and so you're looking for a manifold of this type so that the Ricci curvature is somehow coupled with a metric in this sense. Okay, so actually it's in a stronger sense, and I'll make that remark in the next slide. But for now, just take this to be the definition that lambda is just a smooth function and not necessarily a constant. Okay? So, okay, any questions? Okay, so you might wonder that usually when somebody says something is proportional to something, one typically means that there is a proportionality constant and Q should be a constant times G, not just a function. That lambda should really be a constant. That's what you would expect in most
Sir,
cases naively, right? Yes.
so when you say Lorentzian case, like, do you mean the Minkowski metric?
Yeah. So in the Lorentzian case, the point is that the metric is not going to give you the topology. The underlying topology of R4 or R3, comma 1 is whatever it is. But a lot of these things can be done even when the metric is not always positive definite. So the Lorentzian metric is this 3-1 metric, right? So it's dx square plus dy square plus dz square minus dt square. So you can try to solve for these kind of, you can try to do the same thing that we call Ricci tensor. You can do the same analysis. So the only thing that was involved there was that the metric was non-degenerate, right? So the metric was positive definite was never used, so to speak, to define K, for example. I mean the scalar, see, we took the scalar curvature to be the trace of the linear map K, and to define the linear map K, all you needed was a non-degenerate inner product, so that you can invert Q and solve for K. So a lot of these things go through for pseudo-Riemannian metrics as well, and Lorentzian case is an example of that. So yes. Okay.
So, sir, like what you wanted to say was that even if it is not positive definite, and in that case, the metric, so if the metric is not positive definite, the metric is not Riemannian, still we can have this kind of machinery. That's what you wanted to say.
Yeah. So the point is, see, the like, just look through what we started off with. We define. I'll make a remark explaining more about this a bit later. But the point was in the proof of showing things were independent of the choice of the orthonormal basis. Sorry, we use the fact that the inner product was non-degenerate, and non-degeneracy was crucial in defining the linear map K in terms of Q. The positive
So,
definition of the inner product was never used.
sir, what do you mean by non-degeneracy here?
So non-degeneracy simply means that if you say, one way of thinking about this is the inner product is a bilinear form, and then if you look at the matrix giving that bilinear form, the matrix is invertible, for example. That is the easiest definition. And the matrix for the Lorentzian case is obviously invertible. It's 1, 1, 1, minus 1. Okay. The other way of thinking about it for typical infinite dimensional spaces is that non-degenerate means that given a non-zero V, there exists some W non-zero, so that the inner product BW is non-zero. Okay, so it could be that inner product VV is 0, that is fine, but there should be some W, so that inner product V with W is non-zero. That's what non-degeneracy means. So that you can have a map from V to V star using that inner product. So that's
But sir, if it's the inner product and if VV inner product is 0, then V must be 0, right?
no, but inner product is just a name, right? So I'm saying that inner.
Oh, so you mean a bilinear map? You
Yeah,
meant a bilinear map.
bilinear, which is over C, for example, would be linear in one and skew linear in the other. But the point is that non-degenerate, so a non-degenerate bilinear map. So when I say inner product, I usually mean the more general thing, that you just need every non-zero V to have some W, so that the pairing of V with W is non-zero. The W does not necessarily have to be V itself, which is the usual choice if your inner product is positive definite, right? But it would be a different choice if the inner product was not positive definite. So, like if it was negative definite, that would still be a nice, sort of bilinear form, just that there you want V to pair with minus V. Right? So yeah, so a lot of these things go through for that setting as well. Okay. So, okay, any other questions? Okay, so let me, So for a surface, of course, I keep repeating the example of a surface, but we have seen that for a surface that this Q, the bilinear form Q, and here, of course, the Ricci is the same because 1 over 2 minus 1 is 1. So Q is the same as the Ricci tensor. There's no scaling, and this is nothing but the Gaussian curvature, right? So this is something you've seen. So for a surface, Q is K times G, where K is not a constant. Remember, K is the Gaussian curvature function. So according to this definition, a surface is an Einstein manifold because the function lambda can be taken to be the Gaussian curvature. Okay. Okay. So the remark that I wanted to get to is that the usual notion of proportionality in common man's sense or a street sense is that lambda should be a constant because you typically talk about the constant of proportionality. It turns out that this seemingly weaker definition that we have of lambda to be potentially a function, not necessarily constant, is actually not that weak. In fact, you can show that if there is a function lambda for which q equals lambda g, and the manifold has dimension at least 3, and if the manifold is connected, then the lambda is a constant function. This is something you can show. And actually there's an exercise in Docarmo's book where he highlights the steps needed to prove this. If you're interested, you should go and try to prove that. I'll not prove it, but this can be proven. Okay. So the upshot being that you can take either one of the definitions for manifolds of dimension bigger than or equal to 3 to be the definition of an Einstein manifold. That an Einstein manifold is a manifold for which the bilinear form Q, I mean, so for every P, it's the bilinear form. So the form Q is a constant times the Riemannian metric. Okay? So that you can take that to be the definition. All right. So this is not obvious from the old definition. Okay, let me remind you, this requires some work, but they're equivalent. That's my point. And hence you will see lambda to be a constant as the definition in most references, online or in books. Okay? So you might ask, what about surfaces? We just saw in the first half of this slide that for surfaces, a surface is an Einstein manifold in the old definition. Is it an Einstein manifold in the new definition? Because the Gaussian curvature is usually not a constant for a surface. It's a varying function, correct? So if I want to claim that a Riemann surface, for example, a surface which is orientable and has complex structure and so on, the usual surfaces that you encounter. If I want to claim that a Riemann surface is an Einstein manifold, the first half of this slide is not going to work. Because what I want is a metric G for which Q equals constant times G, correct? I cannot just choose a random metric G and then claim that Q equals Kg, because for a random metric G, the Gaussian curvature is not going to be a constant. So it's not going to be an Einstein manifold according to the stronger definition that lambda has to be a constant. So what do we do there? Well, there comes to our rescue this fact called the uniformization theorem.
Sir, it was frozen for quite some time, the audio, video both, for a few seconds.
So from the remark or up to here?
Yeah, so from the remarks somewhere.
So let me start here. So I'm saying that in the old definition of Einstein manifold, we wanted Q to be lambda times G, where lambda was a smooth function. However, whenever you say something is proportional, you typically expect a constant of proportionality, which means you typically expect lambda to be a constant. And in fact, that is how most references and maybe online references define an Einstein manifold to be. It's a manifold for which Q equals constant times G. Okay? So you might ask, okay, why did we choose the more relaxed definition? Well, it turns out that you can prove that if Q equals lambda times G, where lambda is a smooth function, the dimension of M is at least 3 and M is connected, then lambda is in fact a constant. That is something you can prove. It is not immediate, but there is an exercise outlined in Docarmo where he does that. I would highly encourage you to try to do it if you are interested in how this is proven. Okay. So the two definitions are equivalent for dimensions bigger than or equal to 3 and for connected manifolds. There's a function lambda for which q equals lambda g, or there's a constant c for which q equals cg. They're both equivalent. Okay, good. So the question is, what about dimension 2? We have just seen in the first half that the dimension of the slide, that the dimension 2 case is an Einstein manifold in according to the previous definition. But it will not be an Einstein manifold for any random metric g according to this new definition, because the Gaussian curvature is typically not a constant. It varies, correct? So what do we do? Well, it turns out that there's something called Riemann's uniformization theorem. This is Riemann, enlightening us from a different like field altogether, from complex analysis, which says that for orientable surfaces, every Riemann surface admits a metric of constant curvature. So you might have heard of this theorem in complex analysis, or maybe in some other geometry courses. So this is a very fundamental and uh, important theorem. So it says that there is some metric that you can impose on any Riemann surface such that the metric has constant curvature. Remember, for a surface, constant curvature means constant Gaussian curvature, means constant sectional curvature, means constant Ricci curvature, which means that for this particular metric, the surface does satisfy q equals constant times g. Okay, and this constant is going to be the constant. So every Riemann surface is indeed an Einstein manifold, but you have to choose the metric carefully. You cannot just choose any metric and assume that it is Einstein, because in the new definition, q has to be a constant times g. So the metric has to be chosen very carefully and with care. Okay. Okay. Any questions or comments?
Sir, what do you mean by a Riemann surface?
So, well, a Riemann surface, see, for the most part, a Riemann surface is going to be something which locally has a, so it's a two-dimensional surface, meaning every point has a tangent plane which is a copy of R2. Riemann surface means that the tangent plane has a the tangent plane can be identified with C, so that the action of I on C. So what does I do on C? So there's an action of I on C, right? So if you have a copy of C, then you can talk about action of I, so that if you do it twice, it's -1, right? So Riemann surface is just another way of saying that this is a surface. It's a two-dimensional manifold, but every tangent space can be identified with a copy of C, and then there's an action of I which is compatible globally. So you have this rotation by I at every tangent space. So if you just take an abstract surface, you cannot define it consistently locally in general. It turns out for a surface you can, but if I take an even dimensional manifold, I look at TPM, just because it's R to the 2n doesn't mean I can identify that with Cn and then induce a complex structure on Cn. It has to be done locally, and usually you cannot do it. So a Riemann surface is, I mean, for now, just think of a Riemann surface to be a surface which is orientable. Okay, I mean, that's the simplest definition that I can give you right now. But ideally, what it means is it's a complex manifold of dimension 1. Okay.
So, sir, you said that if there is a manifold which can be, like you said something like it can be, if something can be locally identified to R to the power 2n, it cannot be always identified to C to the power n or something like that. Can you repeat the statement again?
R to the power 2n, see, if I take an even dimensional manifold, it is, the tangent space is obviously R to the power 2n. And there are plenty of ways of identifying R to the power 2n with C to the n, right? The point is that you want to identify locally the tangent spaces to Cn such that the standard action of I on a vector in Cn can be transported to these local identifications on the R to the 2n's in a consistent, continuous way. So usually you cannot do that. You can do it at every point, but how do you ensure that locally around a point, if I take TPM, identify with Cn, I take TP prime M, identify with some other Cn, and these two Cn's are complex vector spaces and they have their own action of I on them, but it has to be done continuously and consistently over the whole manifold, so to speak. So that usually you cannot do, even if your manifold is even dimensional.
And so what do you mean by the action of I to be transported from one point to another? I mean,
This,
what sort of
so
transport?
this is, see, I guess the best thing would be you should read what the definition of a complex manifold is. So locally, you want the charts to be like Cn, and so that when if things are locally Cn, then the tangent spaces naturally look like Cn. And once it's Cn, Cn naturally has an action of I, right? Because given a vector z1, z2, zn, you can multiply that by I coordinate wise. And this is a linear map. It's a complex linear map which squares to -1. So you want these kind of things to happen to your tangent space, but not at a point. You want it to happen locally. So your TPM should have these kind of structures. That's what a complex manifold is.
So I can if I read some text on complex manifold, I can get to know these things.
Yeah,
Like,
I
is
mean,
it
just
the case?
look up the definition of a complex manifold. I mean, there's almost complex. There's a whole bunch of things. But for Riemann surfaces, you don't have to do much. If you allow yourself to assume some theorems, then you can pretty much pretend that this is an orientable surface. Okay. Yeah, I'm just calling it
Okay.
Riemann surfaces because this is really where the theory is heading. So there's no point to not call a spade a spade. So it is called a Riemann surface because these are one-dimensional complex manifolds. Okay. So you should really treat them as such, not just as two-dimensional surfaces, but it turns out that they're essentially equivalent. So orientable surfaces are good enough for this. Okay. So
Thank
yeah.
you, sir.
So in any case, orientable surfaces are also going to be Einstein in the strict sense, but you have to choose your metric with care. Okay. Okay. So in general, you can look for Einstein manifolds or a metric being Einstein for higher dimensional manifolds in dimension 4 onwards, and people do care about these things for various reasons. So let me do one more example, and then I'm going to go on to some motivations behind defining the Ricci curvature and the scalar curvature, and what does it mean geometrically as to what do these things measure. Okay. So let's do the example of Lie groups, since we have spent some time in the last lecture or so talking about this. So we have a Lie group with a bi-invariant metric. Recall that bi-invariant means that you choose an inner product at identity and then you use left translation to define it everywhere. But bi-invariance means that it is also right invariant, meaning if I go to G using left invariance or right invariance, they define the same metric. So not all Lie groups admit such metrics. Compact Lie groups do, but non-abelian, non-compact Lie groups do not. Okay. However, having bi-invariance is quite useful because it gives us a lot of computational liberties. So the curvatures, you pick your favorite, Riemannian, Ricci, sectional, are determined by values at E because of left invariance, correct? So all you have to do is calculate these curvatures at E via left invariant vector fields, and then by left invariance or right invariance, it's the same at every other point, because a left translation or a right translation is an isometry, and an isometry preserves all these curvatures. Okay. So we have seen last time that the Riemann curvature Rxyz for left invariant vector fields xyz has this form. It's 1/4 of the Lie bracket of xy bracket with z. Okay. So if you have the notes with you, or maybe you can go back and read up later on. So this followed from the fact that the Levi-Civita connection nabla satisfied the property that nabla underscore x of y was Lie bracket xy up to a factor of half. And if you iterate this, you basically get this. Okay. Okay. So how do we calculate the sectional curvature? Well, that's very simple. You choose a two-plane sigma. These are all happening at E. Okay. Choose a two-plane sigma. Choose an orthonormal basis xy, which will give rise to left invariant vector fields. So then the sectional curvature we had seen last time is given by 1/4 of the norm square of the Lie bracket of xy. If the Lie bracket of xy was 0, then the sectional curvature would be 0. Otherwise, it's going to be strictly positive. Okay. So the Lie bracket comes into play in a very nice way. So what about the scalar curvature? Well, the scalar curvature turns out to be a constant. Why is it a constant? Because you calculate the scalar curvature at the point E. What should it be? Well, it's 1 over n into n minus 1. There's a factor of 4 here. That comes from the 1/4 from k sigma, but you basically have to take a sum of the sectional curvatures. So what are the sum of the sectional curvatures? Well, it's going to be norm square of EI EJ, where E1 through En is an orthonormal basis of the Lie algebra. Correct? So whatever this quantity is, this is just a global quantity of interest for any Lie algebra. You just choose an orthonormal basis, calculate the mutual Lie bracket, take the norm square, divide by 4n n minus 1. What you get is the scalar curvature. Okay, and that's it. So the scalar curvature, of course, will be a constant, but the point is, because of left invariance, the scalar curvature is going to be this at all points. Okay? Good. So the scalar curvature really doesn't say much here. It's a constant. However, we'll see what the Ricci curvature is. Okay? The sectional curvature is not a constant, as is clear from this formula and the second formula. Okay? So any questions so far? Okay, good. So before we move on to compute the Ricci curvature, note that biinvariance implies, and I remember that I had given this to you as an exercise. So hopefully some of you at least have gone back and done this. This is a very important equality which is used all the time when people talk about biinvariant metric. That biinvariance implies this equality, that it's like y is in the middle. It can either pair with x or it can pair with z, and no matter which side you pair y with, this is the same. So it's like the Lie bracket xy dotted with z is equal to the Lie bracket of yz dotted with x. So y can decide which way to pair, but it's the same output at the end. So this is what biinvariance implies, and we're going to make use of this in the next slide. So just keep this in mind, okay? So what we want is to calculate the Ricci curvature, right? Okay. How do we calculate the Ricci curvature? Well, we simply compute qxx and then divide by n minus 1, because that's really what the Ricci curvature is. So what is qxx? Well, it's nothing but the sum of the sectional curvatures of the plane spanned by x and zi, where zi is going to be an orthonormal basis, right? Okay. So this is going to be 1/4, but now you just write down the Riemann curvature. The Riemann curvature is 1/4 of the Lie bracket. Remember, R x y z was 1/4 Lie bracket x y bracket z. So I'm just supplanting that formula over here. So instead of R x z I x, you simply get this Lie bracket, right? But now, what does biinvariance tell you? So I guess this is a good point to maybe stop and ask if people are indeed following. So biinvariance should be able to simplify this for you. See, biinvariance means that if I treat this x comma zi Lie bracket as one single entity, the middle x can be paired either with the left bracket or it can be paired with zi. That's what biinvariance tells me, right? So by biinvariance, this is the same as this, correct? Because I can pair the middle x either with zi or with Lie bracket x zi. So it is this quantity, but what is this quantity? Well, this quantity is nothing but the norm of Lie bracket x zi squared and sum over I, correct? So the Ricci is going to be 1 over n minus 1 of this quantity, right? So in fact, the Ricci curvature in the direction x at the point E, the identity is 1 over 4n minus 1 summation over I norm square of Lie bracket x with zi. Okay. Any questions? Okay. Good. So all of these are very general computations. You can apply this to any Lie group, provided you know the Lie algebra and you know the inner product. You just simply have to plug it in and you can compute. So this Ricci curvature is not a priori a constant, because if your x changes, the Lie bracket changes and hence the norm changes. But let's apply this to a very concrete example. And perhaps the first example that you can apply this to, in terms of dimension, this is the smallest one. So let's apply this to the group S3 of unit quaternions. Okay? So for those of you who know quaternions, fine. For those of you who do not know quaternions, I think it's a good piece of mathematics, or conceptually a good piece of mathematics to know. In any case, if you don't know what quaternions are, it's good to go back and read it up. Basically, it is R4, but you treat the coordinates not as A, B, C, D, but you treat it as A plus BI plus CJ plus DK. So I, remember, is like the imaginary number I whose square is -1. You introduce two more, J and K. J square is -1, K square is -1. But there's a new multiplication, which is I times J is K, but J times I is -K. So the multiplication is not commutative, but it's associative. Similarly, J times K is I, but K times J is -I. And then you treat an element in R4, instead of A, B, C, D, write it as A plus BI plus CJ plus DK. And there's a usual norm, and then the unit quaternion simply becomes A square plus B square plus C square plus D square is 1. All numbers A, B, C, D of that form. Okay. So it's a very useful thing in geometry and definitely in physics. So it turns out that this group, the unit sphere in R4, S3, is a group because you can pretend that these are unit quaternions and you can multiply quaternions using the rule that I just said. It turns out that this group is also isomorphic to SU2, the special unitary group, meaning these are 2 cross 2 complex matrices which satisfy A times A star is equal to identity. Okay? This is like the analog of the special orthogonal matrices. And SU2 is a compact Lie group, or even S3 is compact, so it admits a bi-invariant metric. Okay? So we can apply our theory to this example because it's compact and hence there is a bi-invariant metric. For SU2, in fact,
So, sir, can we think quaternions as some sort of like bilinear form with the multiplication operator being like some sort of bilinear operation?
it's not quite bilinear, right? I mean, if you want, you can think about it, but it's basically see, it's a ring structure, right? So if I give you two quaternions, when you multiply, it's again a quaternion. So it's not really a bilinear form, right? If I give you two quaternions, when you multiply, it's again something of the form A prime plus B prime I plus C prime J plus D prime K, where you can compute A prime, B prime, C prime, D prime. It is really a binary operation, like in the case of a group or a vector space or an algebra. It's just that this is a binary operation which is not commutative, right? Which you would expect in a typical group. However, it is associative, and then you restrict from your viewpoint. Instead of all quaternions, you look at unit quaternions, and the unit quaternions do form almost a group-like thing. It's just that the multiplication is still not commutative, but it has almost all the other properties. Left cancellation, right cancellation, all the properties are there, right? So it's really a binary operation, but not a bilinear map because it's not mapping to R. Right? Okay. So in any case, I mean, people who like SU2 might want to think about SU2, but I mean, there's no reason not to like quaternions. So the point is, there are these elements I, J, K. These are just formally defined so that I square is -1, J square is -1, K square is -1. And it turns out that these elements I, J, K form an orthonormal basis of the tangent space to S3 at E. So when I say E here, I mean the number 1, 0, 0, 0, or the quaternion 1 plus 0i plus 0j plus 0k. Okay? That's the identity of the group. And the left invariant metric is also bi-invariant. One can check these things. You don't have to check it, but if you haven't seen these things, as I said, I mean, just take it as an exercise separate from the course and just try to learn it, because there's no reason to not know this and, like do a course in mathematics. So one can show that the Lie bracket satisfies these equations. And this is also something it will be clear once you see what the group is, that the Lie bracket of ij is 2k, the Lie bracket of jk is 2i, and the Lie bracket of ki is 2j. Because it has this cyclic property. So So exercise really is that assuming all of this, you can now compute the sectional curvature because of the formulas that we just have in this slide itself. And you can show that the sectional curvature equals 1, which implies that the Ricci curvature is, the Ricci tensor actually is going to be equal to the metric G. Okay? Because once the sectional curvatures are constant, whenever you have a manifold of a sectional curvature, we just proved it in the first example, that such a manifold satisfies Q equals lambda G. And lambda has to be necessarily a constant, so Q equals some constant times G. Here it turns out that the constant is basically 1. So the Ricci tensor is actually G itself. Okay. So S3 or SU2 with this metric is an example of an Einstein manifold. So you can treat it either as part of the first example or as part of the Lie group example because it's both. But this is more for the students who are really interested to learn more about the interdisciplinary nature of the topic. This is not a core exercise from the point of view of the course. Okay. So, okay. Any questions regarding the terminology in the exercise or anything that you want clarified? Okay, good. So let me move on. So since we have talked a lot about what these things are and in some examples, it's always good to get down to the roots and write down what it means locally. Especially in Riemannian geometry, you cannot do away by writing things abstractly. So what does it mean to define Ricci and scalar curvature locally? So we choose a local coordinate system x1 through xn around P. We have the coordinate vector fields del j, which is nothing but del by del xj. So we are going to use the notation Rik, and this is again following Docarmo. Rik is going to be nothing but up to a factor of 1 over n minus 1. This is the Ricci curvature, and the Ricci of del I del k at P. So, okay, so it is just 1 over n minus 1 of Q, the bilinear form Q acting on del by del xi, comma del by del xk. Whatever that quantity is, I'm going to call that Ricci of del by del xi, del by del xk, and I'm going to denote that by Rik. Okay? So Rik are simply the coefficients of Q with respect to the coordinate vector fields. Okay, and up to a factor of 1 over n minus 1, that is my Ricci del I del k. Okay, this is our notation. Okay. So the factor of 1 over n minus 1 is crucial. Rik is not the coefficients for the Ricci, but they are the coefficients for Q. So what do we first compute? Well, we compute Q del I del k. What is Q del I del k? By definition, this is summation. See, Q del I del k is basically the trace of the linear map associated to del I del k. How do I calculate the linear map? The trace of the linear map? Well, I choose R del I del j del k. So I basically put del j in 2 slots and sum over j, correct? What I get is Rij kj. Okay. So I have to be a little careful here. When I'm writing this, I am assuming that the xi's are chosen such that at the point P, the del j's form an orthonormal basis, correct? Because when I'm calculating the trace is calculated by choosing an orthonormal basis and then evaluating L of Vi dotted with Vi. So I'm assuming that the del j's at P form an orthonormal basis, which I haven't mentioned it explicitly here. Only then do you get back the sectional curvatures. Okay, okay, you get Rij kj. Okay, otherwise, if the del j's were not an orthonormal basis at P, you would have to rescale by a certain factor. Okay? But nonetheless, if I didn't choose an orthonormal basis, if I calculated with just a general coordinate system with del by del j as my general coordinate vector fields, it will turn out that the Riks can be computed using the inverse of the matrix G, because it's no longer orthonormal, so we have to rescale. Okay? So this is the exercise that the coefficients Rik can be computed by taking the usual Riemann coefficients R, I, J, K, L. Remember, whenever you have I, K are separated by J and L, and these J and L appear in the superscript for G. And G superscript Lj is nothing but the Ljth entry of the inverse of the matrix associated to G. So G itself gives rise to a matrix with entries G underscore Ij. The inverse of that is a matrix with entries G superscript Ij. Okay. So this is an exercise that if you choose a random coordinate where the del j's are not orthonormal at P, then this is what you get. Okay. Is this fine? This is again a simple computation, but you know, just make sure you know how to go back and forth between indices. And again, here I'm using the Einstein summation convention on the right hand side. L and J are repeated and they appear on the top and the bottom. So the right hand side is a sum over J and L. Okay? Whenever this appears in this form, we're going to use the Einstein summation convention. Okay. The left hand side is a number, the right hand side is a sum. Okay. So we know, look, so if you had to really compute things locally, then this is what Rik is, and up to a factor of 1 over n minus 1, this is what the Ricci is. Okay. Okay. So what about scalar curvature? Well, you can do the same thing. The scalar curvature is now going to be the average of the Ricci, which means it's 1 over n into n minus 1 of Rik g to the ik. And if you unravel all of that, this is what you're going to get. Okay. You're going to get 1 over n into n minus 1, but then this quantity. So it's the Riemann coefficients, but then you have to sort of contract that with JL and IK. Again, the order is important. IJKL, but what you get is G raised to IK, G raised to JL, not G raised to IJ, G raised to KL. Okay. So the orders are important because of how we are doing things. So again, we are using the Einstein summation convention. So the right hand side is a sum over I, J, K, and L, all four indices. Okay. So we'll not make much use of this to compute things, but some of you may find this useful depending on where you make use of this. Maybe in relativity, people are using this to compute things. But this is the local structure of what Ricci looks like and what scalar curvature looks like. Okay. Any questions? Okay, so I want to move into the geometric reasons or the geometric motivations and origins of these curvatures. Okay, and so that you get a feel for why one would study these things. I mean, they turn out to be useful at the end, and they're nice quantities nonetheless, because from a linear algebraic point of view, these are very natural quantities to study, as we have seen. Okay, so let's discuss some geometric aspects of these two curvatures. Okay? So recall this famous formula of Riemann, which we had talked about in one of the previous lectures. It was this, right? So we can take the Riemannian metric, look at the coefficients Gij, which are nothing but the Riemannian metric evaluated at del by del xi, del by del xj, and expand it in the Taylor expansion. It looks like the following. It's delta ij minus 1/3 of the Riemann coefficients xk xl plus order 3 terms. Okay. The crucial thing is this is not true for any arbitrary local coordinates. I said that last time and I'll repeat it now. This is only for normal coordinates around P. And I think in a lot of the projects that people are working on and submitting, normal coordinates and these systems are very useful in various computations and lemmas. So this is a system where you look at the exponential map, and the exponential map at P is a local diffeomorphism. You choose a small ball inside TPM, such that the image under the exponential map is a diffeomorphism, and such a coordinate is called a normal coordinate around the point P. So that the radial lines emanating from 0 correspond to geodesics emanating from P. Okay? So in normal coordinates, this formula holds true. So you might ask, okay, we have these Gijs. Once you have a Riemannian metric, you get these Gijs, you can form the matrix, which is also denoted by G. Once you have a matrix, you can calculate the volume form for the manifold, right? So how do you calculate the volume form for a manifold M? Well, this is something if you recall, you have seen this in differential geometry. If I give you this matrix G, then the volume form for M at the point P is nothing but the square root of the determinant of G, meaning you take the matrix formed by Gij, these Gijs, you take its determinant, take its square root, and take the usual dx1 wedge, dx2 wedge, dxn. So that's going to be the volume form at P for the manifold M. In general, this may not just become dx1 wedge, dx2 up to dxn, simply because the square root of the determinant may not be 1. And that's why the local volume form at P will differ from the standard volume form in the Euclidean sense, which is simply dx1 wedge, dx2 up to dxn. Okay? So
So, sir, we define the infinitesimal volume form by taking by generally taking wedge products, right?
no, but the wedge product, see, you cannot just take the wedge product for any chart, because then the thing is going to be independent of the, I mean, it will depend on the chart, right? You cannot just choose a chart and say dx1 wedge, dx2 wedge, dxn is your volume form. Right? So, I mean, if you want to do that, then typically you take a partition of unity and you do that. Yeah, so I guess what I see what you're saying. So you can take local coordinates and then take dx1 up to dxn and then take this, take the partition of unity. So what I'm saying here is, because you have a Riemannian metric, the construction of a Riemannian metric already incorporates the partition of unity. So you don't have to choose a partition of unity to construct a volume form. What you could do is, you could, for every point P, you could choose normal coordinates and then define the volume form at P to be dx1 with dx2 with dxn, where xi's are the normal coordinates, times square root of determinant G at the point X. And one can show that this determines a well-defined n form on M. So in the sense, it patches correctly on overlaps. There's, so this is actually going to turn out to be a globally defined n form, independent of the coordinates, as long as you choose normal coordinates at every point. So
Okay.
what you're suggesting is probably from the abstract point of view of a smooth manifold where there's no metric. But I'm saying, given a metric which already incorporates the partition of unity, you can simply produce a volume form by this method. This takes square root of determinant G, dx1 with dx2 up to dxn at the point P. That's going to be an n form, non-degenerate n form at P. And then this is actually going to be well defined all over M. So the only thing that you have to check is, if I choose two overlaps of normal coordinates, what happens? Well, it turns out they transform exactly correctly, because you're choosing things in the right order. Okay? So this is what people call the Riemannian volume form, but it's contingent on the fact that you have chosen a Riemannian metric. You cannot do this on a smooth manifold unless you have chosen a metric. Okay. So yeah, so that's what I mean by the volume form in this case. So yeah, so the volume form on M is simply denoted by d mu G, because you'll be integrating some function or something over M, and is denoted by d mu G. You can think of mu also as the measure or the mass if you want. So d mu G is nothing but square root of determinant G, dx1 wedge, dx2 wedge, dxn. So there's a wedge here. I haven't written it down, but it's pretty clear that it's a volume form, so it's an n form, so it's not symmetric, it's q-symmetric. Okay. So we want to calculate determinant G and then the square root of that. Okay. So first of all, how should we calculate determinant of G? And if I take determinant of G, that means I'm taking determinant of the matrix where the ijth entry is given by this formula of Riemann. So I don't want to calculate the determinant, but I want an expansion of determinant, right? So what should happen if I expand? Yeah, so in shorthand, this is written as square root determinant G d mu Euclidean, because the xi's are coming from TPM, and these are the standard coordinates in TPM. So dx1 with dx2 up to dxn is just the Euclidean volume form. Okay. So our main interest is to compute this quantity, square root determinant G. Okay. So by expanding the determinant of G, remember the determinant of G happens to have a 1 in the diagonal. I mean, in the matrix of G, there's a 1 on the diagonal. There's no other 1 anywhere off diagonal. Any off diagonal entries of the matrix G already starts with a quadratic term. It's like some Rijkl up to a factor of -1/3 x to the k x to the l. So if you expand the determinant, you'll see that the determinant G is going to be 1. That's because if you multiply all the ones on the diagonal, you get 1. Otherwise, you'd be taking exactly 1 from the diagonal, n minus 1 number of ones from the diagonal, and then 1 Rijkl from the diagonal entry. Right? See, all I'm saying is if you take the determinant of the matrix and expand, you can get the constant only from the ones on the diagonal. You can get a quadratic only from n minus 1 ones on the diagonal and a non-one from the only left diagonal entry, which is what this term is, the second term. And because you're choosing this from the diagonal, I equals j, that's why it's jkjl. Any other term is going to contribute a cubic or higher. This is simply by expanding the determinant, okay? Just make sure that this is, I wanted to leave it as an exercise and I will, but make sure that you understand this. Just go back, think of the matrix in your head, expand it in your head and you'll get it. You don't even have to write things out, okay? So the first two terms comes by expanding the diagonal entries of the matrix, and the extra terms go into the cubic, and any off diagonal combinations will give you cubic and higher. Okay? So this is what determinant G is. So what should happen to square root of determinant G? Because that's the one we are interested in. But before that, can we simplify this somehow? I mean, this summation, does it seem to be simplifiable? R, JK, JL, XK, XL. Can we simplify this somehow?
Sir, the second term has something to do with Ricci scalar, perhaps?
Yeah, so if you think about it, you can just see I'm writing down JKL here. Ideally, I should have just written summation J, but just to be concise, we have JKL. So I can sum over KL after summing over J, correct? It's the same thing. If I sum over J, what do I get? I basically get up to a factor of n minus 1, the Ricci of del K del L in the direction of P, correct? Yeah, so as you said, it's 1 minus n minus 1 over 3 summation over K and L, the Ricci of del K del L times XK XL. So actually at this point I could have removed the summation because the Einstein summation convention applies perfectly fine, because K and L appears at the bottom and at the top. So this is just this, okay? So at this point, you should note that if we hadn't divided by n minus 1 in our original definition, we wouldn't have needed n minus 1 in the numerator here. So this is the reason why some authors choose to not rescale by 1 over n and 1 over n minus 1 in the definition of Ricci and Scalar, so that the n minus 1s don't appear in determinant G. Okay? So, I mean, there's reasons for both definitions. So hopefully you see that now. But since we have chosen with our definition, we'll have to introduce the n minus 1 here, because that is how our Ricci is defined. Okay? So what you see is that when you expand the determinant of G, you basically get 1 minus n minus 1 over 3 times the Ricci curvature is appearing, the Ricci tensor appearing rather, and then third order terms. Okay. So what we are interested in is really square root of determinant G. Right? So what should happen when we take the square root? So think of this as 1 minus a function which is of quadratic and higher. This is like call the whole thing 1 minus this whole thing x, capital X. So we want square root of 1 minus capital X, right?
So a prefix of half will come beside the
Yes,
second
exactly.
term.
So it's just 1 plus half x, and then you'll have some other things going on, right? Yeah, so exactly. So it's just the expansion of, it's the binomial expansion of 1 plus x to the 1 over n. So for sufficiently small x, we can expand that, and then you'll have an extra half because we are taking square root. So what you get is 1 minus n minus 1 over 6, because 3 got multiplied by 2. And we have the Ricci. And here I am employing the Einstein summation convention. So K and L are appearing both super and subscript. So it's sum over K and L, okay? Make sure. And the higher order terms will stay higher order terms. So since we'll choose X to be very small, the higher order terms really don't matter in the long run. Okay? So this is what you get, correct? So any questions on this? So this is simply the expansion of 1 plus y raised to 1/2. for y smaller than. Okay. So what does this give us? This basically gives us something very nice. It tells us that the Riemannian volume form is nothing but 1 minus n minus 1 over 6. These Ricci curvatures scaled by x to the k, x to the l sum over, and higher order terms times the Euclidean volume. So somehow it's telling you that the Riemannian volume for M can be compared to the Euclidean volume, but in the comparison, the Ricci curvatures appear very naturally. Okay, so in somehow they're controlling the directions in which the volume tends to expand or shrink compared to the Euclidean volumes. Okay? So you can compare the metric volume form with the standard Euclidean volume. Okay? So are there any questions with this final equation? So this is something, once you do the red exercise, this is automatic, and this is a nice equation because you see the Ricci tensor appear very naturally in normal coordinates, mind you, which is always in normal coordinates. Okay? So let me end with the final geometric punchline. So imagine that the Ricci curvature at P in the direction of V is positive. So Ricci P V is nothing but Ricci P V comma V. Okay, I'm just making it a shorthand. Ricci P X was nothing but Ricci P X comma X. So if this was positive in some direction V, okay, then this means that that quantity here, Ricci P V comma V, is a positive quantity, and there's already a minus sign here. It is minus of n minus 1 over 6. So what that means is that you can take a small conical region in M obtained by geodesics of length epsilon initialized at P. So you're looking at a solid cone in M obtained by geodesics of length epsilon initialized at P. The initial velocity of each of these geodesics are inside a small cone about V. So see, if you take a vector V and take a small cone around V, so that's going to give you a cone, and then you take geodesics initialized at P with these velocities, go up to length epsilon. What you get is a solid kind of ice cream cone kind of object. So that conical region has a certain mass, has a certain volume. And if you calculate that volume for epsilon suitably small using this metric volume form, you can show that it will have a smaller volume compared to the same conical region in the Euclidean space, simply because there's a minus sign here and the Ricci curvature is positive. Okay. Conversely, if the Ricci curvature along V is negative, this minus and the negative of the Ricci gives you a plus. So the same conical region will actually have more volume than the corresponding conical region in the Euclidean space. Okay. So this is one interpretation of the Ricci curvature being positive or negative in a certain direction. Okay. So there are a lot of things people have done with this line of reasoning, and one can exploit this even further, but this is almost sort of the tip of the iceberg. You can say a lot more about this in so many different ways. So I'll just make this remark. Okay. So let me end regarding the Ricci curvature. Let me end by saying that if Ricci curvature is positive, meaning it's positive at all points and in all directions for all non-zero vectors, so in the strong sense, then positive Ricci curvature has very, very strong topological consequences. And hopefully you'll see some of these theorems in the next lecture. There's quite a few beautiful, deep classical theorems due to Cheeger, Gromol, Myers, and a whole bunch of people. So Ricci curvature being positive has very strong significance, but negative Ricci curvature has no topological consequences for the most part. Okay, so that is very surprising, at least in dimension 3 onwards. But such is the nature of things. Okay. So I want
Sir,
to.
Sir, suppose there is a manifold and we have not yet given any Riemannian metric to the manifold.
Yes.
So now using the wedge product, we can define an infinitesimal volume there in that manifold.
Sure.
Now suppose in the same manifold I give two different Riemannian metrics, and then I get two different kinds of Riemannian volumes. So how does those two Riemannian volumes compare with the infinitesimal volume which I defined using West product in the absence of any Riemannian metric?
I mean, usually they would not be relatable, right? It's just like three independent constructions. Like the one that you use is you construct using a chart is something that you construct using a chart. The one that you construct using a metric is intrinsic to that metric, so to speak. So usually they're just like two entirely different things. I mean, I wouldn't expect any relation whatsoever. It's like saying you
So
process and you construct something. Well, that's a volume form. You could easily see, even if you take a metric G, you could easily scale the metric everywhere by 2, and then the volume form changes altogether, right? Or you can,
so we can use all these three types of infinitesimal volumes for as a measure of volume integration, as a measure of integration in that manifold.
yeah, because see the volume itself. Yeah, just a second. See the volume itself doesn't. See, volume form is see it's a misplaced word in my opinion, because whenever you say a volume form, usually you mean that uh, it's an n form. It's a top dimensional form which is nowhere vanishing on the manifold. That's what you mean by a volume form, right? But a volume form by itself is kind of meaningless, because if you choose a metric, that metric helps you measure the volume of the manifold, and if I scale the metric by 2, then of course the volume form is going to change. The volume of the manifold is also going to change, right? But just take the sphere, take the standard metric, but if I scale the metric by c, then of course the volume of the sphere is going to change. It's not going to be the same, right? And if I choose a general volume form without any metric or whatever, then it's just a general volume form. So there's no relationship between the two. Usually the point is that in Riemannian geometry, at least, that once you specify a metric, you want to understand various properties associated to that metric, which could be curvatures, which could be volumes, which could be the mass, all sorts of things. But if you change metrics, then of course the whole thing changes altogether. So I mean, in a lot of these instances, the question is sort of in the reverse direction. That if I give you a manifold satisfying certain hypotheses, is there always a metric with positive Ricci curvature, for example? You can ask this question, and this is a hard question, because once you have a manifold with positive Ricci curvature for some metric, then that manifold has to satisfy some topological property. It cannot just be an arbitrary manifold. So usually the question goes the other way, that you're trying to find a metric having certain properties in terms of its Ricci curvature or sectional curvature or something. I mean, just a volume form on its own is almost like a differential topological construction, not really a geometric construction. Right? It just uses partition of unity and local charts. There's no geometry in the construction of a n form in the way that you see in differential geometry.
So, sir, say for three dimensions, so for R3, the infinitesimal volume element dx dy dz, this happen in this particular case. It happens to be the volume element formed by West product as well as the Euclidean volume element, right?
Yes, but that just depends, right? So I mean, that's because you're choosing x, y, z to be standard coordinates. If I choose 2x, 3y, 6z to be my standard coordinates, then my volume form is going to be 36 dx dy dz, right? It's just a choice, right? I mean, if I impose R3 with a drastically different Riemannian metric, the volume form is going to be different. See, I mean,
Okay.
the point is that if I take the volume form defined using a metric, like I just said, then that depends on the metric. There's nothing you can do about it, right? If I change the metric even by scaling, the volume form changes. That's just simple geometry. So, I mean, if I choose two different metrics, they'll have two different volume forms. How they're related, that then wants to study how the metrics are related or what related things go in between. In general, you cannot expect any kind of relationship in general, because two different metrics will have two different sectional curvatures, two different Ricci curvatures, two different scalar curvatures. So there's no reason to believe that they will be related in some way. They probably wouldn't be, right? So yeah, so that's the thing. So I mean, the questions that you ask regarding what you want to do with the volume form have to be very specifically designed to take into account the geometry, and then the Riemannian geometry can give you answers depending on the kind of questions that you have. Right? So, any other questions? Okay, so yeah, so I want to make, so I think this is more like a historical slide, historical remark that Ricci curvature, as you have seen, appears already in general relativity. It appears in Scalar geometry, but from a mathematician's point of view, Ricci curvature appears in the so-called Ricci flow equation, and this is a very powerful and standard technique nowadays in modern geometry. So the Ricci flow equation is a set of equations introduced by Richard Hamilton in 1982. So Hamilton's main observation was that the Ricci flow equation, this is basically a geometric analog to the heat equation, whatever that means, has the property that it tends to simplify the structure of a manifold. Okay? And I'll intentionally not be very specific regarding the things I say here because it would take me away from what I want to say, and I'm definitely not expert on these things. But it helps to simplify the geometric structure of a manifold in terms of certain curvatures. Okay, so one expects that Ricci flow, Ricci flow is a flow which governs how the metric deforms over time, how the Riemannian metric deforms over time. Okay? And the actual equation is d by dt of gt is equal to minus 2 Ricci. But anyway, forget that equation. It's a flow which governs how the Riemannian metric deforms over time. And one expects that in the limit, the Riemannian metric which is produced by this flow is either Einstein or of constant curvature. This is, of course, too good to be true. Usually this is not true. And usually you run into problems, but one has to study all of that and see whether the Ricci flow exists for all times, makes sense, whether singularity is developed. But it's a very powerful tool because of this expectation that it produces a metric in the limit under deformation, which is a nice metric. Okay? So informally, what is Ricci flow? Well, it's a process of stretching a given metric G over time in directions of negative Ricci curvature and contracting the metric in directions of positive Ricci curvature. So it sort of tends to homogenize the metric in terms of the Ricci curvature. Okay, that's what it informally tries to do. So a very specific instance is in 2 dimensions. If you write down the Ricci flow equation, the Ricci flow ends up doing exactly what the uniformization theorem does. It ends up endowing the manifold with a metric of constant curvature. So you can get a new proof of the uniformization theorem using Ricci flow for dimension 2. Okay. There are several books out now where they talk about these basic things as well as the whole theory. The key thing was that the Ricci flow method, along with an analysis of singularities and surgery, was applied very, very successfully by Grigori Perelman. I'm sure all of you know about his work and the story behind it and the story after it, to prove the geometrization conjecture, which was a big insight into the land of three-manifold geometry by Thurston, which in particular implies Poincare conjecture. Okay. So, in fact, it is really one of the most impressive achievements in modern mathematics. Like the things you have to combine and the knowledge that you have to make this successfully work. But it's a very powerful and important tool nowadays for modern Riemannian geometry. So Ricci flow is important. I mean, Ricci curvature in particular is important for several reasons. Okay. So yeah, any remarks or comments? This is more like slide.
Perelman actually declined the Millennium Prize which he was offered after solving this.
Yeah, so even so I mean all that is known. So because he has his own style of working and his own sort of values of evaluating how people perceive things. So yeah, so that is that. But this work is nonetheless a great piece of work. So okay, so let us end with what scalar curvature is. So now that you have seen what Ricci curvature is, at least somewhat geometrically, what is scalar curvature? Well, the scalar curvature, if it's positive at a point P, what happens? You look at a volume of a small ball about P, take a small ball, center P, radius R, calculate the volume of this ball using the measure d mu g, which we just introduced. You can compare the volume of this ball to the volume of a similar ball in Euclidean space. So you can compare the volumes, right? It will turn out that if the scalar curvature is positive, then the volume of the ball in the manifold is smaller than the volume of the ball in the Euclidean space. A particular example is compare the area of a disk around the North Pole in S2 with a standard disk in R2. You see that the disk around the North Pole has smaller area than the standard flat disk in R2. Similarly, when the scalar curvature is negative at a point P, the volume of a small ball is larger compared to an Euclidean ball. An example is, again, take a hyperbolic plane, the upper half plane, take a disk around I, compare that with a standard disk in R2. And the disk around I is going to have more area, okay? So you can actually show, and I'll not prove this to you, but again, these are things which are really beyond the scope of the course. And for those interested, you should read up Gallard, Huling, Lafonte, or other texts like Peterson. So if you compare the volumes, this is a volume of radius epsilon around P, this is a volume of radius epsilon around 0, then it looks like 1 minus this K of P is the scalar curvature, epsilon square appears, there's no linear term, and then there are these constants, n into n minus 1 divided by 6, n plus 2. Again, the n into n minus 1 appears because we have divided our scalar curvature by 1 into n minus 1 in our definition. If we hadn't done that, then this wouldn't have appeared. The numerator would have been 1. Okay, and that's again the reason to normalize versus not normalize. Nonetheless, so this explicitly tells you that volume is small or bigger depends on the sign of the scalar curvature. So let me end with this remark. So this is like connecting back to one of the things that Swapnil had asked, and I was saying that you can define it for pseudo-Riemannian. The curvature tensor that we have talked about, or the Ricci tensor, can be defined for any connection. Okay, that has nothing to do with the metric, because we never used metric compatibility or torsion freeness to do a lot of these basic properties. Okay, to prove that the Riemannian connection is unique, you need torsion free and metric compatible. But the basic properties and the definition of Ricci tensor and the curvature tensor can be done for any connection. However, the key difference is that the scalar curvature requires a metric, because a scalar curvature really requires an inner product. The inner product needs to be non-degenerate. It could be Riemannian or pseudo-Riemannian. So Lorentzian is perfectly fine, but it requires a metric. The other two things do not require a metric. Okay? Just make this distinction in your mind. So let me, since this didn't have many exercises, let me end with this small exercise. It's a very easy exercise, and I hope all of you will do this. Show that the scalar curvature of M cross N, which is the product Riemannian manifold, is the sum of the scalar curvatures. So armed with this, you can now compute scalar curvatures of lots of manifolds. Okay? So the scalar curvature of a product is the sum of the scalar curvatures. Okay? Okay, any questions? So this is the end of it. If there are any questions or any comments, I'd like to hear them. Okay, so if there are no more comments or remarks,